Hey math fans, Alex here, and in the last video we did a lot with joint distributions, including how to find the probability of a region of the sample space, how to find a marginal distribution of just a single variable from the joint, and we talked about independence. Okay, so today we're going to work through a couple of more interesting examples, and we'll start off with example 4. So suppose 2 points, which we're going to call x1 and x2, are tossed at random and independently onto a line segment of length capital L. What is the probability that the distance between the 2 points does not exceed little l, which is clearly less than capital L? Okay, so just to kind of paint a picture, so if this is like a number line, and without loss of generality, we'll go ahead and start this at 0, and start this at capital L, so it has length L. And if I pick the points at random, maybe I pick maybe this is x2, and randomly I pick this is x1. And perhaps this length right here is lowercase l. Well, in this case, I've achieved a success because the distance between here is clearly less than lowercase l. Okay, but if I do the same thing, 0 to capital L, and this time I randomly have the points like really far apart. This is x1 and this is x2. This is still capital L. Well, the same distance. Okay, this is little l. Well, clearly this is a fail because the distance between x1 and x2 exceeds capital L. Okay, so this is a fail. Okay, so how are we going to do this? Well, we're going to go ahead and suppose that the point x1, x2 is going to go ahead and be in a total region B, where B is going to be given by the square of length L, so 0 to L cross 0 to L, right? Because x1 is between 0 and L, and x2 is also between 0 and L, so hopefully that makes sense. And what we want to find is we want to find the probability that the distance between x2 and x1 does not exceed L, so that means that it's less than or equal to little l. Okay, but unfortunately in this setup, we can't directly find that probability because I only taught you how to find the probability of a subset of the region B. So what we're going to need to do is we're going to need to sketch the xy plane, or the x1, x2 plane, and come up with the region described by this probability. That's going to be a common theme today. Okay, so let's go ahead and do that. I'm going to go ahead and draw a graph. This is going to represent the x1 axis, and this will represent the x2 axis. Okay, and then this is going to represent our total region, which is the square of length L. And we're going to figure out what this region is. Okay, well, if x2 and x1 are within L of each other, properties of inequalities says that this implies that x2 minus x1 is going to be between minus L and positive L. But then I can go ahead and add x1 to all sides. Add x1 to all sides, and then I get, let's see, this will be x1 plus L, less than or equal to x2, less than or equal to x1, or sorry, this should be a minus L. Okay. Now, imagine that this was a y and that these were x's, and essentially you have inequalities to graph. And the first one to graph is, x2 is maybe less than or equal to x1 plus L. And you would also graph x2 is bigger than or equal to x1 minus L. And when you shade the regions, hopefully something should make sense. Okay, so let's go ahead and graph that up here. So the first condition is that, x2 is less than or equal to x1 plus L. Okay, but that's going to be a graph. Maybe I'll do this in like a lowercase blue. That graph is going to go ahead and have a y-intercept of lowercase l, which I'm just going to plot right here. This is lowercase l. And likewise, we're going to need that over here, so I'm going to just plot that as lowercase l. Same distance away, right? Those are the same. So that's the y-intercept, and then it's going to have a slope of 1, right? Because this is the independent variable. Okay, so I'm going to try to sketch. Yeah, that looks to be about a slope of 1. Okay, and we know that x2 is less than or equal to that. So keep that in mind. That's going to be where we shade. The next graph, which I'll do in maybe a darker blue, says that x2 is bigger than or equal to x1 minus l. So we can imagine is that, there will be an L like all the way kind of down here. Okay, that's going to trace out that region. Okay, but we don't really need this region outside of the box, so I'm just going to kind of remove it. All right, and then the region that we're going to shade is what? Well, it's going to be less than this line, but greater than this line. Okay, so it's going to be this region right here. Okay, that's the region that we're interested in. And I'm going to go ahead and call that region, maybe we'll call this region A. And now what I'm going to do is I'm going to actually go ahead and save this because we're going to use it a couple of times. So, all right. So now I've just turned this problem into a different kind of question. What I've done was now I've said that the probability that x2 minus x1 is less than or equal to L. I turned it into equivalent problem. The probability that the ordered pair x1 comma x2 is in the region A, okay, where A is the following region. Okay, now I'm just going to go ahead and paste the region from before. And now hopefully we might be able to kind of integrate this a little easier. Okay, however, if we want to find the joint distribution, that's actually going to be pretty easy in this case. Okay. The reason being is both x1 and x2 are tossed randomly, so they're going to have uniform continuous distributions. Okay, so p x1 of x1 is going to be, well, let's see, it's going to be anywhere from 0 to L, so it's going to be 1 over the length, which is L. And of course, this only works if x1 is between 0 and L. You can write it out as a piecewise function if you want, but and the distribution for x2 is going to be similarly 1 over L. And since these were tossed independently of each other, that means that the joint distribution, so p x1, x2 of x1, x2, we discussed in the last episode that this was just going to be the product of these PDFs, which was just 1 over L times 1 over L, which is 1 over L squared. So now we should be able to integrate this fairly easily, okay, because there's no dependence on x1 or x2 whatsoever. Okay, so we have that the probability that the ordered pair x1, x2 lives in A, that's going to be the double integral over the region A of the PDF of the joint distribution dx1 dx2. Right? But what I can do now is I can pull this constant out of my integral, and really dx1 and dx2 is really the same as, dA. It's just another way of writing it. So this is thus going to equal 1 over L squared times the integral over the region A dA, but that's just the area of the region A. This this is going to be 1 over L squared times the area of what we've called region A. So all that's left to do is find the area of region A. So I'm going to go ahead and paste this one last time so we can find that. Okay, so it's a little easier to find the region actually of these triangles right here and just subtract that from the squares area. Okay, so what we're going to have is that the area of A, which maybe I should write as, I don't know, this weird, right, 1, 2, 3, 4, 5, yeah, this is a hexagon, believe it or not. Doesn't look like a hexagon, but the area of that is just going to be the area of the square minus the area of these two triangles. So that triangle plus that triangle, which you'll notice is actually going to make up a square. Okay, so this is the area that we've denoted A. Okay, so what's the area of the whole square? Well, that's just going to be L times L, which is L squared. Now, what's the area of these two triangles put together? Well, let's see. So if I put these together, notice that, this distance right here, that distance is going to be L minus L, because this is also going to be L. Right? So if that's true, then we have that the area of these two put together is just going to be a square with side length capital L minus L, or you can take it as two triangles. You can do this however you want, but this is going to essentially be capital L minus lowercase l squared. Right? So now I have a difference of two squares, which can be written as the first thing minus the second thing times the first thing plus the second thing. Okay, where this is going to just get me a positive L, and this is going to get me 2L minus lowercase l, which gets me 2LL minus L squared. Okay, so now we're almost done. We found the area of A, and now notice that the probability that I'm interested in is just that area times this 1 over L squared factor. Okay, so the probability that x1, x2 is in A is just going to be this divided by L squared. Okay, so I'm going to box that because that is the answer. Now, I want to make a couple of remarks about this answer. The first remark that I would like to make is notice that this was actually the same thing as just the area of the region that I was interested in. No surprise there, we spent a while computing that. But then I'm dividing by, this is the area of the entire sample space region. It's the area of what I've designated B. Okay, so it turns out that this is a special kind of distribution where you're taking two continuous uniform distributions that are independent. So this is actually called a bivariate, because there are two variables, uniform continuous distributions. Whoops. Okay, so this works for these cases. This formula always works, and it's nice to get to kind of skip all this integration stuff and just figure out what the areas are. Okay, so that's that example. Let's move on to the next one. All right, example 5 is Buffon's needle problem. So Buffon was a natural scientist, I believe the 18th century. And I don't know too much about his life, but I do know that when he worked for the University of Paris, he had some realistic theories about geology and ecology that violated religion at the time, so the University of Paris made him recant those statements. So it's kind of sad, but he did introduce a lot of calculus into probability theory, so he said, suppose a plane is ruled with parallel lines a distance of capital L apart, and you just throw needles. Okay, and those needles have to, of course, be smaller than capital L, but a success in this case is going to be if you throw the needle and it's going to be between two of the horizontal lines, and a failure is going to be otherwise. Now, technically, the lines can be any orientation, but since they're all parallel, you can just rotate the plane until they're all horizontal, which is easier to visualize. So we want to know the probability that a tossed needle will not intersect one of the parallel lines. Okay, so probability is something like this and not something like that. Okay, so to start this problem off, I'm actually going to take one of these little sections and I'm just going to zoom in. So maybe we'll do like this and this, where this length is capital L. Okay, and let's perhaps consider a needle. And just because I've been doing it in green, I'll try to stay consistent. What are two parameters that are going to characterize whether or not they fall in the gap or not? Okay, that's kind of a bad needle, but you get the picture. Well, it turns out that there are going to be two parameters. You might think that capital L is the only thing needed. However, that's not true. Capital L can be as long as you want, as long as the angle from the horizontal is sufficiently small. The distance between the angle of the horizontal and the needle, as long as that's sufficiently small. Okay, so there's some kind of angle component. Okay, so this angle is, which we'll call theta, is clearly important. The other thing that's going to be important is the distance from the point of the needle to probably the closer distance to the horizontal lines. Okay, so this perpendicular distance we'll probably call x. Okay, and the whole thing has a length of L. So the idea is going to be what? Well, maybe I should put x over here. So let's see. I want to say, this angle right here, it's theta. This distance we'll call x. And we can actually go ahead and figure out this horizontal distance as well. Okay. And note that if the needle is actually fully inside these horizontal lines, that's going to mean what? Well, it's going to mean that this distance is going to be smaller than this distance. Okay, so what is this distance? Well, if the whole needle has length L, then trigonometry tells us that this length is going to be L times the sine of theta. Now, x and theta as parameters, we can say that x and theta are both random and independent random variables with distribution that is uniformly continuous. Right? If they're independent, they have no relationship with each other. But then separately, that horizontal distance can be from 0 to L. So I'll just write that down. So let's see, x is anywhere from 0 to L, uniformly continuous. And theta is going to be between what? Well, it's going to be between 0 and 180 degrees because we're measuring the angle from this horizontal. And if the angle were like, I don't know, clearly maybe the needle were like over there, well, we would just maybe use this as the horizontal and just only count the positive angle. Okay, so really we can just consider that to be in 0 to pi because we're using radians. And these are uniformly continuous. And the probability of success the probability of success is going to be, okay, so let's go back up to this picture again. So if the needle intersects one of these horizontal lines, that occurs whenever this L sine of theta is just bigger than x. Okay, where x is going to be the horizontal distance from this end of the needle to the closest horizontal line to it. Okay, so technically this would be the distance, which is going to be equivalent to that distance. Okay, so in other words, we have a failure whenever L sine theta is larger than x. So clearly a success is going to occur if the inequality is flipped the other way around. Okay, so we want to find, the probability, that L sine theta is less than or equal to x. Okay, so to do that, we're going to have to kind of figure out what the PDF is going to be. And then we're going to have to shade the appropriate region and figure out what that region is. Okay, so it's not going to be too bad. Note that, if these are our random variables, they're each going to have probability distribution functions, which we can go ahead and write down. So we know that px of x is just going to be 1 over this distance, which is L. And the probability distribution for theta is just going to be 1 over this distance, which is pi. So the probability of their joint distribution, remember, because x and theta are completely independent, that's just going to be the product of these probability density functions. Okay, so we get 1 over L times pi. Okay. Now, we have to figure out what the entire region is, and then we can use the results from the previous problem to just take the area of that divided by L pi, which is the total area of the sample space. Okay, so let's go and sketch a graph. Okay, so maybe we'll let this be the theta plane, and we'll let this be the x plane. And I'm going to take this condition, and we're going to graph it and figure out what's going on here. Okay, so what this is I have, let's see, x is greater than or equal to L sine theta. So maybe we should actually graph x equals L sine of theta and figure out what that is. Okay, well, that's essentially going to be a sine curve with period pi. Okay, so this is going to be point pi. This is going to be the point L, and this right here is going to be the amplitude, which is lowercase l. Okay, so this is our entire sample space region B, right? This entire rectangle, that's going to be, B or whatever. And what we're wanting is the area that x is going to be greater than or equal to that curve. So really what we're wanting is our region A is going to be this highlighted portion. Okay. So all we have to do is find that area and then divide it by the area of the whole rectangle, and then we're done. Okay, well, that area is a little trickier than the previous problem, where we are actually going to have to integrate something. But the thing that we're going to integrate is the area under this curve. Because if we can find that, then the thing that we want is just the area of the rectangle minus that region. So I've just generated the probability now, and I've defined the probability of L sine theta being less than or equal to x. That's going to be the same thing as the probability that the ordered pair theta comma x is in a region which I'll call A, okay, where A is, maybe I should copy this, where A is this region. Okay. Okay. So how do we find this area so then we can subtract it from the whole thing? Well, we're just going to integrate. Okay, so to find A, or the area of A, we're just going to take the entire thing, so this whole entire rectangle, area of the rectangle, minus the area of, let's see, that curve. Okay? Well, the area of the rectangle is just going to be L times pi. And the area of this, well, that's going to be an integral from 0 to pi of, let's see, this function. Okay, so we're going to integrate from x equals 0, or yes, sorry. Yeah, no, theta equals 0 to theta equals pi of L sine of theta d theta. Okay. Which, you know, you can pull the L out and you can evaluate this integral fairly easily. And when you do that, you're going to get that it's going to be let's see, 2L. Okay. So what we have is that the probability that, I forgot if I put theta, I think theta went first, theta x is in the region A, well, that's just going to be the area of A divided by the area of the entire region B, which I know I really haven't defined, but the area of B is just the rectangle. So this is going to be L pi minus 2L divided by the total region, which was L pi. It's bivariate continuous uniforms. We have that same idea. Okay. Now, a couple of remarks that I would like to make about this one, because this is where things get a little juicy. Okay, so remarks. Okay, so number one, if, you know, this L pi minus 2L over L pi was the probability of the needle not touching one of the lines, then, you know, what's the probability that it is going to touch the lines? Well, that's going to be 2L divided by L pi. So that is the probability of the needle touching. Also, it's the theoretical probability of the needle touching. Why am I emphasizing that that's the theoretical probability? Well, going back to chapter 1, if you'll recall, the theoretical probability equals the experimental probability for large enough n, where n is the number of trials in your experimental probability. So what I can say now is that the theoretical probability of 2L divided by L pi, that has to equal, or I guess maybe approximate, the experimental probability. But the experimental probability is going to be, the number of ways in which the event actually happens when you run the trial. Okay, so I've already used A and B, so maybe C, divided by the total number of trials, where C is the event that the needle touches the lines. Okay, so why is this interesting? Because I can now solve this little equation right here. I can solve this guy for pi. And if I do that, I get my second and potentially most important remark, which is that pi can be approximated by running multiple trials and by taking 2 times the length of the needle divided by the length of the gap, which is completely arbitrary and up to you, by the way, times the total number of trials divided by the number of successes. And because I thought this was so cool, I went ahead and wrote some code in Python to actually simulate this to show you that this wasn't made up. So I'll be right back where I go ahead and do that. And we're back. So if you're here, you might be here because you're continuing to watch the video in its entirety, or you might be a little interested in the clickbait in the thumbnail. Either way, the idea behind Buffon's needle problem is you have a table or a plane with all these spacings right here of length capital L. Okay, and I'm just going to toss a needle that has length less than capital L. I'm just going to toss it on this table right here. Okay, so maybe it's going to look something like this. And I'm interested to know kind of the probability that the needle is going to touch one of these lines. Okay, so in this case, it looks like it's not touching. Okay, but if I orient it maybe a little differently with the same length of needle, in that case it is touching. So I wrote a computer program in Python to not simulate the probability, so to speak. We already calculated that before, but to actually see if we can approximate pi with this. Okay, so if you look at the program, pretty simple stuff. This is the width between the horizontal lines. This is the length of the needle, number of trials that you're interested in. Basically, this condition forces you to make sure that lowercase l is less than capital L. And then this total is basically the total number of successes, where a success is defined actually as the needle touching one of the horizontal lines that you drew. Okay, so if this condition is met, and of course see the previous part of the video if you want to know where this comes from, then you add 1 to the total, and then we're going to go ahead and run a little counter and print the total at the end, and then we're going to see if we can approximate pi. So let's go ahead and run this guy. Okay, so what is the length of the spacing between the lines? You can pick whatever you want. Okay, I'm going to be unusual. Usually I pick 10, but we'll pick 6. Length of the needle, 2.5. I don't know. And how many trials do you want to run? Let's just start off easy with 10 trials. Okay, so these numbers are pseudo-random numbers between 0 and 6. Okay, these numbers are going to be between 0 and pi. Again, watch the previous part of the video for info on that. And this represents whether or not it was a success. So it looks like in this case it was not a success. In this case it was, so total was 1. This was a failure because total is still 1. Here is a success, so we increased it. Success, 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 fail, success. So it looks like 7 successes out of 10 trials, 70%, but we don't care about that. We care about this formula right here, plugging that in, which has nothing to do with pi, by the way. Right? These are lengths that you pick. N is the number of trials, which again you pick, and this is basically the number of successes. Everything is within your control to pick here in this little simulation, and we get that pi is approximately 2.78. That's a pretty awful approximation, right? Okay, so what's the solution to this? You might know. Run more trials. And because the number of trials is going to get pretty bad, I'm just going to go ahead and comment that out so we don't have to see it all. What did I do before? 6, 2.5, and maybe this time we'll do maybe 50 trials. Oh, God, it prints that out. Well, whatever. We get 2.6 for our approximation of pi. That's still pretty bad, right? Okay, I wanted to print, okay, interesting. Why is it printing all of that? Let's see. Okay, there we go. Okay, so this time I ran 100 trials, and it looks like our approximation is at least kind of close to 3, 2.98. But 100 trials is not infinite trials, so we have to keep going. Okay, so 6, 2.5, and I'm going to try 1,000 trials. And we still get about 2.98, which is still not great for an approximation. So let's up the ante a little bit. So 6, 2.5. We're going to do 1,000,000 trials. This might take a minute. Ooh, that's juicy. 3.148. Okay, and that's just 1,000,000 trials. I might try 10 million trials. I know 100 million trials like took over 5 minutes, but I'm going to go ahead and try one more just for the viewers. 6, 2.5. Okay, so 7 zeros here. Okay, and while we're waiting for that, this is Buffon's needle problem. And yeah, so you can actually physically approximate pi with a simulation of just throwing needles on a table. It's actually pretty neat. And I might skip ahead to when this actually computes the approximation for pi. Okay, I didn't have to skip. 3.141. Again, that's super interesting. So yeah, pi can be approximated by throwing needles on a table. Okay, let's go back to our last example. All right, let's tackle this last example. It's kind of an important one, and it pops up every now and again. It says, given independent random variables x and y with PDFs given here, find the PDF of the random variable z, which is equivalent to x plus y. Okay, so the first thing that I'll do is I'll note that the joint PDF of x and y is given by pxy of little x and little y, but since x and y are independent, that's going to be the product of these individual PDFs. Okay? And this is since x and y are independent. Now, what we're also going to do is we're going to go ahead and say that z is a function of x and y, okay? But being a function of x and y, we can kind of replace y and note that since z is equal to x plus y, that implies that y is equal to z minus x. Okay, so this function of x and y can actually just be written as a function of x and z minus x. Okay, so what's the PDF going to look like now? Well, remember that the PDF is going to look something like this, where we're going to integrate over all z of pxx and pyy, right? And we're going to integrate that with respect to z, ideally, right? Okay, because we're going to integrate the joint over all possible values of z. And ideally, you know, the joint distribution should be in terms of z, and we're going to get some kind of formula. But we can actually go ahead and do a couple of things. The first thing we can do is we can replace the PDF of y with the PDF of z minus x. And now everything is in terms of x, which means that instead of integrating over all z, that's actually going to be equivalent to integrating over all values of x, because it's the same thing. If I integrate over minus infinity to positive infinity of x, well, z is just the sum of x and y doesn't matter. I'm still going through all the possible values of z. Okay, so this is going to be probability of x times the probability. I still call this y, but instead of little y, I replace that with a z minus an x. Okay, and I'm integrating that with respect to with respect to x. Okay, so this is technically the answer. I can't do any more than this. The only thing I will do is I'm going to go ahead and change the bounds to be x equals minus infinity to x equals positive infinity, just to make it look a little cleaner. But other than that, that is the probability density of z. Okay, so in general, this is kind of my answer, though it looks a little strange. So I do want to comment on a couple of things. So from maybe differential equations, maybe you've seen something like this before. This is the same as, the convolution, which is symbolized like this, evaluated at z. Okay, so this is the convolution function, and you usually use it Fourier analysis and making Laplace transforms a little easier. But yeah, that's the convolution function. Now, let's go ahead and do a practical example to end this off, just to kind of show you how you would go about computing such an integral. Because in general, it's not easy. All right, let's do an example where we actually compute a convolution. So we're going to find the PDF of the random variable z, which is going to be the sum of random variables x and y, where x and y are both uniformly continuous over the same interval 0 to 1. So first thing to note is we should probably write down the PDFs of x and y, which are pretty straightforward. They're uniform continuous, which means it's 1 over the length of the interval, which is 1. So it's going to be 1 if x is between 0 and 1, and 0 otherwise. And the PDF of y is going to be the exact same. It's going to be 1 if y is between 0 and 1, and 0 otherwise. Now, we already have a form for what z is going to be, so let's go ahead and write that down. So the density of z is going to be the integral. Let's just remind ourselves what the formula is. It's going to be the integral over all x to x equals positive infinity, the probability density function of x, times the probability density function of y, but remember y was just z minus x, and this is with respect to x. Now, if we're integrating over all possible x values, we're going to go ahead and use the fact that this is only non-zero when x is between 0 and 1. Okay? So we're going to have that the bounds are going to go ahead and be from x equals 0 to x equals 1 of 1 times probability density of y. Okay? And the goal right now is to figure out how to evaluate this. I'm going to tell you right now, this is going to be a piecewise function. Okay, that's going to depend on a couple of cases for z. All right, so let's figure out what this is. So, case 1. Because remember, this probability density function is of z, so we're considering different possibilities for z. Well, the first possibility is that z is between 0 and 1. Okay, and you can do this a couple of different ways. I'm going to just sketch out a region because that's what we've been doing. Okay, so if we sketch out a region, this is 1, this is 1. Okay, and the idea is that the function is going to basically be over this guy. And if z is between 0 and 1, we're just going to go ahead and let it be any kind of point right here. Maybe call that z. And then if you remember, if x plus y is equal to z, that means that y is equal to z minus x, where this is a constant. Okay, it's something between 0 and 1. And now, using slope-intercept form, we can graph this pretty painlessly. And it's going to look a little something like that, where this is also z. So, what are the possibilities for x? Well, x is going to go from 0 all the way up to z. it cannot possibly exceed z. And if you think about it for a second, that makes sense. X has to be less than or equal to the sum of x and y, which is what z is. Okay, so in case 1, we have that the bounds are going to be from x equals 0 all the way up to not 1, but z, which then ranges from 0 to 1. Okay, so then this is going to be the probability density function of y, but this probability density function of y is just going to be 1 whenever z minus x is in the acceptable bounds, which according to this picture, it is. Right, so this is just going to be 1 dx, which is going to equal z. All right. Now, case 2 is a little trickier, but we could have a situation where z is between 0 and 1. Then we have to ask ourselves what the bound on x could be. Okay, x could be 0.5, for example. Okay, but x needs to depend on what z is. All right, so let's go ahead and graph the region again. Okay, that was a horrible line. All right, that wasn't much better. All right, so we're again going to have 1 and 1, but this time we're going to have that our function is outside of the bounds. The reason being, z is now going to be greater than 1. So we still have that y is going to be z minus x. Okay, but in this case, z is going to be somewhere up here. Okay, and it's going to go ahead and split this up. Just pretend like that's straight for a second. Okay, and then what is the smallest possible value of x for which z fits comfortably inside our bounds? Well, that's going to be this x value right here. Okay, going all the way up to 1. So what is that x value going to be? Well, all we have to do is intersect the lines z minus x and 1. We just have to intersect z minus x and 1, basically setting them equal to each other. Okay, so we're going to have z minus x equaling 1. Well, that's going to imply that x is going to be z minus 1. Okay, so this is going to be z minus 1. And we're integrating from here all the way to this point, which is 1. Okay, so our bounds for our integral have to be from x equals z minus 1 all the way up to 1. Still going to be 1 dx. And when you do that, you're going to get, let's see, 1 minus z minus 1, which is going to equal 2 minus c. Okay, so we get this if z is between 0 and 1, and if we get this if z is between that should 1 and 2. Okay, so we can put it all together, and we have that the probability density function of z is going to be kind of this triple piecewise function, where it's going to be z if z is between 0 and 1. It's going to be 2 minus z if z is between 1 and 2, and it's going to be 0 otherwise. And if you graph this PDF, you're going to get that it's a triangular region, which kind of makes sense. Okay, so a graph of the PDF is going to look something like this. So it's going to start off looking like this, and it's going to peak, and then it's going to go back down. Okay, so why does that make sense? Well, you're more likely to have z, or you're more likely that x and y is going to sum up to something around 1. Okay, so this is more likely than the endpoints. Because at the endpoints, you know, for something very small, both x and y have to be small, and for something big, both x and y have to be big. At least for here, you have a lot of different possibilities, and, you know, I'm going to go ahead and refer you to the video that we did, the first video, where we talked about Demer's paradox, in which if you roll 3 die, it's far more likely to get, say, an 11 than a 3. Okay, so getting to that sweet spot. It's not going to be exactly in the middle, but that's kind of a discrete version of this triangular distribution. Okay, so hopefully that helps, and I'll see you in the next video.